and welcome back to our audit kickoff streams. My name is Jess and we have another exciting project that has just launched on the CodeHawks platform 1 hour ago. So this code base is going to be live on CodeHawks for 1 week, so you need to dig your teeth in and see what vulnerabilities that you can find in there. We do have Anne joining us today to walk through that code base with us, teach us how to set it up and to tell us any areas where we should pay a little bit more attention to, because it may be a little bit more likely that the vulnerabilities could be there. So make sure to stay tuned if you are taking part in this contest. It's really helpful to hear what the developers have got to say. Before we do get into that though, please don't forget, if you have any questions, please let us know in the comments and we will go through those at the end of today's stream. And if you have any throughout the rest of the week, head over to our Discord where we will be answering any questions, both the Cyfrin team and the Swan team as well. So before we get started, let's just read what this protocol is about. So Swan is structured like a market where buyers are AI agents. By setting parameters like backstory, behavior, and objective, you find how your agent will act. By using the budget you deposit, the agent buys the best items listed based on how aligned they are with its parameters. With each new asset bought, the agent's state changes and the simulation evolves. So the code base for this is now live. It's just over 1,000 NSLOC and the prize pool is $21,000. So to get into this a little bit more, I would like to welcome to the stage Erhan. Please introduce yourself.
Hi everyone. Hope you have a bugful and bountiful week with this contest. It's really exciting. So I'm one of the contract authors and I'll just take a tour of this entire thing. Swan, and it also has an LLM Oracle in, so it's like two things. We'll go over all of them and hopefully explain everything in a clear and concise way.
Brilliant. Let's get started. Let's run straight into that code base. So I'll share your screen on here now. Please walk us through.
All right, so I will start with the LLM Oracle because it can be thought of as a separate entity on its own, and Swan uses it in its logic internally. So the Oracle is similar to how other Oracles work. There's a coordinated contract that people make requests, and the coordinated contract is listened by Oracle nodes that are outside. And here we have, let's go like this. First of all, we have a registry contract. So to be an Oracle yourself, to have a node that is listening to this contract and to be able to answer it, you need to be registered to this contract. And it's a simple staking contract. Like there's a stake amount for both generator and validator. And once you deposit this amount, you stake it in this contract, you are basically registered. And that's all you need to do here. The Oracle coordinator itself handles the task dispatching. So just hold on. Let me close some notifications here. Yeah. So first, this is an upgradable contract. So there's this initialize. You will see familiar stuff here. We gathered the administrative stuff into a different contract called Oracle Manager. So it's just some setters for parameters, and there's a fee logic here that I'll get to in a moment, and just base fee units, also some parameters like difficulty, validation factors. We'll get to all of them. But all you have to know here is that this manager contract simply bundles them up so that it's easier to read. So in the contract, what the user does as an Oracle requester is simply call this request function with the input, models, and the protocol. Within the context of this contest, Swan sets this parameter for us, so we don't have to care about it. But it's basically like a metadata for the Oracle nodes to do like, hey, do I need to do some extra stuff after getting the LLM output? Like, do I need to ABI encode something so that the contract can read it? Things like that is given by this protocol value. So the input is simply a string. You can think like, what is 2 plus 2 is an input here. And the models is a list of models that you want the LLM Oracle to use, like GPT-4 or Mini, for example. And the parameters here are the difficulty, number of generations, and number of validations. So you basically say, hey, I want 3 different oracles to generate an output for me, and I want 4 validators to validate all of them. So there are like 12 validations in total. And this validation simply checks like, is this input and output, do they make sense, or did some oracle try to do some malicious stuff? So you provide these parameters as well. And in Swan, these are given by the Swan contract. So you don't touch these at all. So there's just some fee logic here. Like there's a fee for this that you can calculate from parameters. We'll get to that in a moment. Oh, you check that if you have balance and allowance for that. And then the coordinator contract gets that fee from you. And then there are some events emitted for this request. And this is the request itself gets stored on the state. And that's all. That's all you need to do a request. And these are listened by Oracle nodes. It is open source, by the way. It is written in Rust. The link is in the README as well. But you can treat it as a black box for this scope of this contest. So there are two types of oracles. One that does generation, so the one that actually generates an output for you that you expect. Those oracles will call respond function. So here you see that there's a modifier that ensures that a generator is responding to this. And it also ensures that the task that is being responded to is actually pending generation. So I said, like, I could have said I want 3 generation responses for my request. So when I have only 1 generation, this is still pending. But at the 3rd generation, this will change. So people won't be able to respond to this anymore. And while responding, they provide the output itself and the metadata. So the output can be the LLM output on its own, but you can also do some encoding, like some post-processing to it, which we mentioned just a moment ago with the protocol. In such cases, you can provide the output itself in metadata, and the actual output that you encoded can be given here in a much more shorter way. And then there's a nonce here. So what is that nonce? Oracles do a proof of work, a really simple proof of work, like the one in Bitcoin, like you have a hash value that's supposed to be smaller than some difficulty. So they do this to make the responses a bit more difficult to fake. Like they need to spend some resources to respond to it. And I can show you the proof of work part here. Let's see. So this assert valid nonce here. This function handles that proof of work. So there's an ABI encode packed here. It simply packs the task ID, the input of it, the requesting address, the responding address, and the nonce. So that's the message. And then there's a difficulty given in the task parameters. So it's a simple hash-based difficulty check. So this must pass for a response to be valid. And that's why we have a nonce like that. Of course, we check that this generator did not respond before. We check the nonce, and then we store the response in memory, in storage later as well. And then there's a check again here to see if enough response has been made so that we can update the task status. So then we also said we might have validations. We might want validations too. But that's optional. In Swan, we do have validations, but for Oracle itself, it can be 0 depending on the application. So you can only ask for generations if you want. In that case, the task is completed immediately, and then you can send the generator can have the reward immediately without any validations. But let's go on with the validation case. So now all generations has been made, and the task status is updated to pending validation. So now Oracle nodes that are also registered as a validator hear about this event update and then say, okay, now I can validate the responses there. So what they will do is they will collect the generations, and for each generation, they will give a score. And they will also provide the metadata. So what this score means is that like the LLM itself is looking at the input. Let's say we said what is 2 plus 2, and the output was 5. So the LLM looks at both of them and says, hey, this is a bad response. It has nothing to do with the actual question. And then it will output a number, a string, but we will cast it to a number, and we will multiply it so that it's representable within the world of a contract. So like you can think of format ether or parse ether. So 1.0, it becomes like a 1 ether here. And that will be the score of the generation. So some generations will have high score, some lower, some maybe 0 if they don't make sense at all. And the metadata can have the reasoning behind it, where the LLM actually explains why it gave that score to people. The logic is similar to the generation response. They have to be registered as the validator. The task must be pending. They can't validate their own responses, so that's an extra check here. which is done here. They also need to respond with a nonce, similar to the previous one. And then we update the scores. And if the task is completed, it is updated as well. But now there's this finalized validation stuff, which I think is the most attention requiring part here, that we have bugs. Here we do some statistics, really simple stuff. We look at the generations and we look at their scores. So first we calculate the standard deviation from these scores, like all the scores generations that you might think. Actually, I can pull up a quick drawing here, like free-handed. Just think of a simple bell curve. Like let's say the average score is around here. Like we have some generations, let's say 0.5. Just an example, but to give the idea. Let's say one generation was here, another generation was here. Some people got really good answers and they got validated really high scores. Like let's say there were 5 generations here. So then we look at the standard deviation here. Let's say like this. And this like 1 away and 2 away. Just a simple bell curve. So what the function, this finalized validation does is, it computes the standard deviation, the mean. It also calculates the mean from the values that are within a certain standard deviation, like just one of them here. So what it translates to is that it only calculates the mean of these two for this example. And then it only considers their scores. And also while sending rewards, it checks that mean. And there's a deviation factor here, so that you need to be some certain steps away from the mean of the from the standard deviation to get a reward. Otherwise, you're an outlier and your answer doesn't deserve a reward. So we either send you a reward here or do not send based on the standard deviation and the mean. And here, the statistics library is simply used for this purpose. Just some average variance, standard deviation, and the square root function here. And that's basically it for Oracle. So like this doesn't need drawing, just standard deviation and a certain mean difference here. And there's a utility function that get best response, returns the highest performing result from the generations. Well, that's Oracle. So we can move on to Swan. So like Jess described, Swan is a marketplace where the buyers are AI agents. So now you got the spoilers. The AI agents are operated by the Oracle themselves. And as a user, you can create a buyer in Swan. Let's go to create buyer. And it's just a simple wrapper call. We have a buyer agent factory that simply forwards these and also sends the Swan's address itself to the function there. And emits an event for the marketplace services like our backend to pick up that this happened. And then it returns you the address. So this name and description is like, you can think of this buyer as a AI agent, like it has a character. Let's say you're creating Gandalf and the name is Gandalf and description is like he's a magician, he wears this, he likes to buy magic items, whatever. You literally just write a string. There's a royalty value here. So you can, this must be a value between 1 and 0. It's a percentage. So when people are selling you stuff, they're listing you stuff, like just making a listing, they have to pay a fee upfront, and that value is based here. So that percentage is given here. And then there's an amount per round. So Gandalf, that like we just created, can only spend so much money per round. And so what is a round? Let's get to that. Actually, should I show here? Yeah, let me go through the manager actually. So I'm kind of freehanding this. I hope it's not confusing when it's live like this. At least so again, Swan Manager is similar to Oracle Manager. We handle the administrative stuff here. So each buyer, when they're created, so imagine like again, let's go to here. Imagine that this is the time. So I created a buyer here, buyer B. So this timestamp here will be the creation time of the buyer. So this is stored in the contract as in the buyer. There's where is it created at? So it's immutable. This is stored in the buyer contract. So from this point on, each buyer will have rounds that are split into 3 phases. Let's go like this. So round 1, round 2, and each round is split into 3 phases. So first, the sell phase. So when the buyer is first created, during the sell phase, people can sell stuff to this buyer. And by sell, we mean like make a listing. They don't actually sell it to them. They just make a listing, and this will be seen by the AI agent afterwards. They do this through the list function here. So again, like we had Gandalf, so I want to sell him a really cool looking magic stick so that he can do better magic damage or whatever. So I can like do this name itself can be magic stick, symbol itself can be anything. The description is important because it will be read by the AI agent and be deemed worthy or not based on it. Again, the price itself and the buyer address is here as well. So this is different than a normal listing where you can list to anyone and people can offer a price on it. In Swan, you list the item to a specific buyer only. Only that buyer can buy it, and if it doesn't want to buy it, it won't buy it. So you can't sell it to someone else during the same round, or even in later rounds as well. So here is Gandalf's address in this case, and we check that the buyer has the round of the buyer. The phase of the buyer is in sell phase. So basically confirm that, yeah, we are here currently, so we can sell it. And then we simply store the listing itself. An important thing to note here is that the asset itself is created within this transaction. So again, in a normal NFT marketplace, you could have an NFT and you could later sell it. But here, the asset itself gets created when you call this function. And Swan asset is a simple contract. It's a ERC21. But again, it's not like an actual NFT. The total supply is 1, and it's minted immediately to the owner. This is kind of like a design choice. It really looks cool in the block explorers because it looks like a token transfer as an NFT transfer, but actually it's just an asset that exists in the world of the AI agent itself. So coming back, and then there's a transfer royalties part here. So that royalty thing, the asset price itself gets multiplied by the royalty fee. So this royalty fee is taken by the buyer. So when I was creating Gandalf, I set 1 as the royalty fee. So that's like 1%. And the price of it was $100, 100 Ethereum, whatever. I immediately send $1 to Gandalf. But then I also get a platform fee from him. And this is given by the market parameters from the magic contract as well. And then some transfers here. There could be a bug here if the token is malicious. So also good point to note that. And that's all with the listing. Simple as that. Relist function is the almost same, almost copy paste, but now you can list the same asset. So let me get back to here. Jumping ahead, let's say Gandalf didn't like my magic stick, so he didn't buy it. In a different round, I can relist this to a different buyer, like just the same thing. Maybe a different buyer exists here. And in fact, they have a different time instead of the same one. So then if Gandalf didn't buy the item here, now I can relist it to some other buyer that is also in the sell phase. The code is really similar, so I'm skipping this as well. We also mentioned this. We will get to purchase. Should I get it now? Yeah. Okay, so the actual magic happens during the purchase and withdraw phases. So now let's say, okay, I'm selling an asset here, like asset 1. Actually, let's say good magic, and this is Gandalf. Wow, I drew that. Okay. So Gandalf wants to buy good magic, and he was in sell phase. I sold it, I listed it, but now he's in buy phase. And the length of these phases, by the way, is given by the Swan manager. these intervals. So sell interval, like the seconds itself, is stored here. This can be updated while Swan is live. That is some part that we really try to take care of, but it deserves attention, because if you change the round intervals, like let's say instead of 5 seconds here, if I make it 10, suddenly first round is coinciding with the second round of the previous phase. So like, how do you manage the round counts there? We simply made it so that when you change the market parameters, everyone gets a new round automatically, and they're in the sell phase of it. But yeah, that takes recovery and attention. So during the buy phase, now as the owner of Gandalf, or as a cron Swan operator, I need to call make an Oracle request. And I do that with this Oracle purchase request. I provide a prompt here. This prompt is prepared by our services in the current phase. A malicious buyer can give a bad input here, and this was listed in the known issues as well. But you can consider that the input is actually valid here, and it lists the inventory of the buyer, it lists the magic itself, a backstory of the Gandalf and whatever, and also good models here. And by only authorized, we mean like either the buyer, owner of this buyer, or an operator of Swan can call this. And this simply calls the request function from the coordinator. Now, when this request is made, we return the task ID from Swan coordinator, and that task ID is stored in the Oracle purchase requests. So now, after that, we can call a purchase function, and note that we are still in the buy phase. We confirm that we are in the still buy phase. And we get the task ID from that previous call, and now we can actually read that result. ABI decoded as a list of addresses, which actually mean which assets am I buying. And then I will call purchase function on Swan for each these assets. So here is the call that we make there. And if you go to purchase here, again, I confirm that the listing that I want to buy is actually being called by me. So that check is done here. And then some money transfers are happening here along with the token itself. And that's all we have for the purchase function. So coming back, if everything goes well, the task is completed. So this also means that you don't have to call purchase again. It checks that, which will revert if you do here. And that's all about the buy phase. So now let's say we bought the magic. So Gandalf now has good magic, and we move on to withdraw phase. One thing I didn't mention so far is that during those two phases, the owner of Gandalf, which is a contract itself, and the owner is an account, EOA to be specific, they can't withdraw the money that they have deposited in the buyer contract. Because if they were able to do so, like I could make a LLM request and then withdraw all my money, so the request doesn't make sense anymore. Maybe I don't have enough money to buy the assets that are coming from the Oracle. So we prevent that by having a separate phase to withdraw money. And we do something else during this phase. Just like the Oracle purchase request and the calling purchase in the buyer agent, we will call Oracle state request. The code is almost exactly the same, just different parameters. Could even be a one function with a one if else, but like a different function here. And what this does is it has a different protocol name as well. So the state of the buyer is like the result of simulation. So let's say Gandalf was going to war, and I sold him a really good magic. So now maybe he had an enemy that he couldn't defeat so far, but with good magic, he is able to defeat it. So now he keeps a diary, and this diary is updated on chain in the state variable, which is done by this Oracle state request. So you make the request to LLMs, again, input and models. Same thing applies here. Like we have a prompt for this. We prepare the input. A malicious buyer can say, hey, Gandalf, go learn coding and completely change the story of the narrative. But again, we don't expect that here. And then after that request is completed, we check that we are in withdraw phase again and update the state. As simple as that. And again, this withdraw function will allow you to actually withdraw money from the agent, and this is only called in withdraw phase. There is also this minimum fund amount, which we described while creating the buyer. So there's a specific amount that needs to be kept for the next sell phase. And that is checked here as well. One thing that you should be looking at in particular is how the phase is computed. So like you have the t. Oh wait, okay, that's weird. So you have t prime here, the creation of Gandalf, and then let's say at this point you made a call and you want to know which state are you in. So what you have to do is like you compute a difference here, like how long has it been, like also what is the cycle time. So how many cycles have there been? So there's one cycle. Okay, so I'm in the second cycle. So how long has it been during this cycle? Okay, it says be this much. So is this lower than the cell interval phase? So that's true. Okay, then I'm in the cell phase. So you need to, this check is done for each call, each phase check, and that whole logic is handled here. Also, a similar example is given here. It's kind of straightforward actually, not too complicated. But if there's a bug here, it will mess up everything else. Oh yeah, this part in particular. So like because we might update market parameters in Swan from time to time. And like I said, that might mess up with the round count. So we ensure that that doesn't happen here by processing each market parameter on their own and then adding up the results here. So yeah, this part requires an attention. And I think that is all with the buyer agent. We also covered the Swan asset. Yeah, that's all.
Amazing. Thank you very much for that run through. That was very useful for the auditors that will be taking a look at this code base this week. So there, Han has covered the code base in detail and some specific areas to watch out for. So if you are taking part, make sure to pay close attention to those aspects in that video. So as I mentioned at the start of the stream, it's a $21,000 prize pool. It's just over 1,000 lines of code, and it's a really interesting code base. So do make sure to check that out. If you do have any questions throughout the week, head over to our Discord, and there is a special channel for this contest where you can ask questions and be part of that community. Lots of auditors will be in there asking questions, so you can hear the feedback they're getting, and you can ask your own questions in there as well. But that is all we are doing on today's stream. So thank you very much, Erhan, for coming onto this live stream today. That has been valuable for those auditors, and I can't wait to see what they find in the next week.
Yeah, likewise. Good
Amazing.
luck, everyone.
Yeah, good luck, and we will see you soon. Thank you very much for joining.
Bye-bye.